Let's get started. Well, this is Computing with PubSub, and your speaker is Vinny.
Thank you. So my name is Vinny Ramesh. I'm co-founder at Ikigai Labs, and Andy, who's going to be presenting with me, couldn't make it today. But so we started this work a couple of years ago during grad school. During when I was in grad school at MIT. And Andy is still at MIT, kind of continuing some of that work. And we're at Ikigai, we're kind of working on commercializing this to make better, easier to use data tools, and I can talk about that later. So just quick overview. I'll give you a little bit of motivation and a high level kind of idea of where we're going with this work and kind of what prompted us to get started. Talk about this factor graph computational framework that we actually created, how we implement it during Redis, using Redis, and then also results and real-world case studies. And I haven't told you what this actually does yet, so just bear with me for a second. Cool. So this entire line of work started a couple of years ago when we were trying to build distributed algorithms to solve really, really hard optimization problems, right? In particular, we were interested in integer optimization problems, and an example being if you want to optimize truck dispatches, right? You can't send out half a truck. You have to send out a truck, or you don't send out a truck, right? So these types of integer optimization problems are really, really hard to scale and build reliable algorithms for. Right. So that's kind of where we started, and there had been some theoretical work that you could use probabilistic approaches to solving these, and that's kind of where we started. In particular, there's this, in the field of probabilistic inference, there's this data structure called factor graphs that have seen a lot of use there, and in fact, each and every one of you today is benefiting from one. It's a data structure that's on each one of your phones. It's behind every single error correct, or most error correcting codes out there, GPS, image processing, and so on. So outside of this community, not a ton of people have heard about it, but it's very ubiquitous. So we wanted to see, hey, can we use this data structure to solve these really, really hard optimization problems? Because right now, if you want to solve integer optimization problems, you have to use one tool. You have to understand 100 million different approximation algorithms. If you want to use linear optimization, whole nother tool set, and so on. This just results in very, very hard to manage different systems, and writing these in a distributed manner is really, really complicated. So that's where we started, and what we actually found out during the course of this work is we can actually write any algorithm in this kind of using what's called factor graphs. And it turns out it's really a gossip kind of language, and anything from machine learning to linear algebra to optimization to graph analytics can actually be represented in this framework. And it gives us an automatically distributed implementation for all of these algorithms out there. So you can just write the algorithm in one place. You don't have to worry about whether it's a centralized implementation or distributed implementation. It takes care of all that for you. And the actual communication happens behind the scenes via PubSub. Right? And the idea is you can write this algorithm once and run it anywhere, and the only thing you have to change is which PubSub system you actually use end of the day. So let me make this a little bit more concrete. Right? So this is an example of a factor graph, and there's really only a few things you have to keep track of here. One is it has, it's a bipartite graph, so that means there's two types of nodes. You have what are called variable nodes and factor nodes, right? Each variable node has some sort of state associated with it, and computation on these graphs happens when variables nodes communicate messages to factor nodes and vice versa, right? So this is all we're really working with, and part of what we showed is, hey, it's actually possible to implement any algorithm on top of these graphs, and because the graph is already distributed, you get an automatic distributed representation. So bear with me if with the equations and everything, I'll kind of just give you like an idea of what they actually mean at a high level. So Let's now kind of define what computation on these graphs look like. So it's basically a gossip protocol, right? You just have to define what messages are sent back and forth between nodes. And again, we can represent any algorithm in this way, which was actually surprising to us. So the idea is whenever a node receives a message from one of its neighbors, it performs some sort of update function, which is specific to the algorithm that you're implementing. And then it computes kind of a new message and then sends that back out to all of its neighbors. And then you just kind of keep iterating this process, and we can solve many of these problems. And I'm not going to go into the proof, but we were actually able to show that this kind of gossip language is Turing complete. So any algorithm can be implemented. It's not super easy to implement everything, but for a lot of popular algorithms, you're able to give succinct representations. So again, just bear with me with the math for a little bit. I'll just kind of give a high-level representation of, or high-level overview of what it actually means, and then jump into some code here. So the first kind of application that I was talking about earlier is we want to perform some sort of probabilistic inference. And this is actually one of the initial use cases of factor graphs, and the idea is you just have to define two types of messages, right? One is if you're a variable node, all you do is multiply all your incoming messages, and then if you're a factor node, all you do is take a particular type of weighted average of all your incoming messages. So those are the only two operations you have to specify, and then you can have a distributed probabilistic inference algorithm on top of these graphs. Another example that's super popular in central algorithm in machine learning is stochastic gradient descent. So it turns out any stochastic gradient descent algorithm has an automatic representation, distributed representation on top of factor graphs. And really, again, what the math is saying is, again, for any variable node, you just take an average of all its incoming messages, and all of the kind of variables you're trying to optimize turn into variable nodes in this case. And then your, basically your factor nodes are the components of this objective function that you're actually trying to optimize. So what this is saying, look, for every variable node, just take an average of all your incoming messages from your neighbors. And then from every factor node, just take the message you just received and subtract basically the derivative or of the component of the function that you're associated with, right? And another kind of, this is a simpler example, is we can also represent matrix multiplication, another central algorithm in this framework. So again, for basically every factor node, it's just saying, multiply your incoming messages, and then for every variable node, just sum up your incoming messages, right? So the first part is actually, okay, figuring out how do you take a particular algorithm or problem and convert it into this graph structure. So again, like I said, in stochastic gradient descent, or any optimization problem, for example, your variables become your variable nodes, and your constraints roughly map to your factor nodes, right? So what we saw is like, look, we want to basically implement this continuous iterative gossip across these nodes. And how do we do that, right? So when we first actually built the system, it was just a single-threaded, implementation in Python, and we used it to, for example, solve Sudoku puzzles and that sort of thing, and that was fun, but it didn't really scale. So the next thing we tried was actually, hey, can we, implement this kind of iterative communication between nodes or computation between nodes in Spark, right? And that was interesting. We were able to get it to work for certain sizes, but once you get into a lot of this kind of very iterative computation, so if you want an algorithm to converge, you basically are going through thousands upon thousands of iterations, and Spark really wasn't meant for that. It's kind of meant for these MapReduce type computations, but once you get into these super iterative computations, both kind of managing and writing state to disk, keeping in memory, keeping track of lineage, all gets really complicated. So the thing we tried after that was actually, well, why don't we just try PubSub, right? And I had actually been using Redis I've been using Redis since probably 2010, 2011, so I was pretty familiar with the entire system, and I was like, okay, why don't we use Redis PubSub as our first implementation? So we actually built the first version of this entire system with Redis PubSub as the communication layer between nodes to perform these computations. So at a very high level, what any program looks like in this in the factor graph computation framework is first you have the actual algorithm that you want to compute, which is the program here. Then you have the factor graphical model, which is the factor graph of your problem representation. And then under that is your actual PubSub system that runs the communication back and forth between these different nodes. And the idea is you can just write the program and the factor graph kind of once, and then you can take that to different environments or locations just by swapping out the PubSub. So if you want to run it just on your laptop, you can run it on Redis PubSub. If you want to run it on a super heavy cluster, then you can switch it to Apache or Google PubSub or AWS or Lambda functions or anything like that, right? And all of that without actually changing the Python code or the factor graph representation. So the idea is like, look, even though it's the trade-off we're getting is it's slightly more difficult to write algorithms in this language, but it gives you a framework for getting a distributed representation of anything that you can take from your sandbox environment to production and scale it without actually having to worry about how do you write distributed versions of these very difficult computational algorithms. So basically at a high level, how we actually run this is, and I'll walk through a few examples as well, is you initialize the PubSub system given the data about the problem, which kind of turns into like what does the graph look like of the problem, for example, of the optimization problem that you're trying to compute. What are all the variable nodes? What are all the factor nodes? You can just write what the update functions are. Take it into that. We create the factor graph representation, and kind of going back to here, we actually just encode the entire factor graph in the PubSub system. So all the edges of the graph are just channels. And then each node is both a publisher and a subscriber. So it subscribes to the appropriate edge channel. And then it publishes once it receives a message as a callback back to its neighbors. So I'll talk a little bit about what these interfaces look like. So now it gets a bit more concrete. So basically, the first thing we want to define is the interface between writing a program and the actual factor graph itself. So let's say we want to run an algorithm called sum product, which is a very popular one for kind of probabilistic inference. All I have to do is specify this is the variable node function and this is the factor node function, nothing else, and I can have a fully distributed representation. So the entirety of code on top of this system, if I want to basically build an optimization solver, is to write a little bit of code for sum product, and this is saying, hey, for every variable node, this is what we want you to run as your callback function when you receive a message through Redis PubSub. And again, for every factor node, this is what you need to run as your function when you receive a callback on Redis PubSub, right? So these two are all I need to write, and I automatically have a distributed optimization solver that can scale to as many machines as you want. So now the next kind of interface I'll talk a little bit about is the interface between this factor graph representation of the data and the PubSub system itself. So there's really only kind of three functions that need to be defined here. So this is just basically what does any node do when it receives a published message, right, as its callback. So there's basically three things. One is it receives a message, updates its own internal state, computes what its outgoing messages are to its neighbors, and that's basically runs one of these functions here that you've specified. And then it just propagates that message, which is just a publish, right? So basically in Redis, each node it basically implements this message pass wrapper for Redis. So the idea is you basically have update node cache, which is just updating the state once it receives basically a callback in Redis, meaning it received a published message that it was through a channel it was subscribed to. Then we just compute the outgoing message based on the particular algorithm that you're running. And 3, we just propagate that message to all the appropriate neighbors. And I don't have to specify much here because which neighbors you're propagating to is all just kind of specified by which channels you're subscribed to. Right? So most of the information is actually just encoded in the PubSub system itself. The PubSub basically through the channels and subscribers encodes the entire topology of the graph. So all we have to do is specify, hey, this is the callback, and then in whatever kind of language, such as Python, and then this is the algorithm I want each node to run. Right. So I'll run through kind of a few case studies and results of what we've actually accomplished and how it compares to the state of the art, right? So like I said, when we started this work, we wanted to see if, hey, can we implement or invent new distributed optimization algorithms based on some probabilistic methods. So we want to take advantage of, there's some theory earlier on showing that, hey, some of those algorithms like sum product, max product can be used to solve optimization problems, but no one had really implemented it or come up with an algorithm to do so at scale. So that's really where we started with this work, is how can we solve these super, super hard integer optimization problems using probabilistic methods. So the idea is we can use what's called we can represent any optimization problem as a probability distribution, and then we can run these inference algorithms. So now the hard part is, okay, how do you convert any optimization problem into the factor graph representation? So the idea is every variable you're optimizing over becomes a variable node, and every constraint that you're optimizing over is a factor node. So this is my entire optimization solver that I've written. So it does everything. It's distributed because it just runs on Redis PubSub on the interfaces I mentioned before. I can scale it to as many cores or processes or machines as I want. And it will solve any linear, integer, discrete optimization problem. And this is really all that you need to do so. And what's going on is, so a little bit about, so the actual results, like that's awesome, but we have a succinct, algorithm that can do all of this, but how does it compare to the state of the art, right? So we basically ran 3 types of benchmark. One is on very easy optimization problems, and by that I mean those where we already know what the result is supposed to be. Hard optimization problems, which are, we can't solve them instantaneously. They probably take a day or so to solve. And then challenge problems are problems where no one actually knows what the solution is. Like, how well do we compare with the state-of-the-art solvers, right? This first chart is basically showing the error for the easy optimization problems, and Gurobi is pretty much the best optimization solver out there. So this is, our implementation is unoptimized. It's running on Redis 100% as the PubSub system, and we're basically approaching almost exactly the same error rate as the state-of-the-art optimization solver out there. For the hard problem, we don't quite get the best result, but we get a second feasible result as the best solver out there. And then for the challenge problem, the one where no one actually knows the result, we come up with a integer kind of solution, whereas Gurobi is not able to. It just switches back to kind of the relaxed kind of linear optimization solution. So in that sense, for some of these really, really hard problems, our solver is actually able to approximate it much better than the traditional state-of-the-art solutions out there. So another kind of interesting example that we ran that you might know of is PageRank. So we have a super large graph. We want to compute the PageRank of each node. How can we do it in this framework very easily? So PageRank, the way to convert a regular graph to a factor graph for PageRank is just take every node in the original graph is a variable node, and every edge in the original graph is a factor node, and then we can do this gossip and run PageRank. So this is my PageRank code. So again, this is all I had to write, and I have a completely distributed implementation of PageRank that runs in parallel. And because we're running it on top of PubSub, we don't actually have to worry about how the communication happens. This, as programmers, literally all you need to write. So this implementation, so our best implementation was actually in C, and then this was for a 400 or 120 million node graph, 468 million edge graph, and Ligra is another kind of benchmark out there, and we were able to approach almost the exact same results in terms of running PageRank as one of the best systems out there. And Ligra is a system that's built just for graph computation, whereas our system is kind of general purpose, but we're still able to get very, very compelling results. And this is running on kind of 32 threads. So as a programmer, I didn't have to worry anything about how do I worry about distributing the computation or anything. The kind of PubSub behind the scenes takes care of all of that. So, and then the kind of final kind of benchmark we ran is singular value decomposition. So this is at the heart of many kind of machine learning algorithms and lots of algorithms in total. So basically what you're doing is you're just doing iterative matrix multiplication. That's really what singular value, the main operation in singular value decomposition is. And we compared it to Spark. So this is in a paper published about Spark, they ran it on 68 executors, so that's about on 68 machine cluster. We ran it on a single machine with 32 threads, and we were able to achieve almost, very, very similar results. So 0.98 seconds versus 0.2 to actually compute singular value decomposition. So, and the actual algorithm for singular value decomposition is almost the same as the PageRank algorithm I showed. So, with, I haven't modified anything about the code, just like I can just change the parallelism, I just changed the algorithm, and the underlying system is actually performing as best, almost close to the state of the art as the best optimization solver out there, best graph computation framework out there, and also Spark for distributed computation as well. So kind of quick on future directions and kind of where we're going with this work. So we're able to show that, hey, this is awesome. We're able to do a ton of almost unrelated computations on the single framework, provide a language that gives you automatic distributed computation, writes these algorithms in a distributed way. Where do we go from here? So we actually want to expand this to GPU computation. It's great that we can run it on cores on your laptop, but can we actually get in CUDA and run it in a distributed manner on GPUs? We want to get towards implementation of reinforcement learning. So a lot of the optimization algorithms, the reason we were so interested from the very beginning is that's what a lot of reinforcement learning is based on. So what we're working on now is writing the right programs for reinforcement learning in this language. So that gives us an automatic distributed algorithm for reinforcement learning. And then you can take it to, what we're also interested in is some work in kind of, can you train on one environment and just by switching out the PubSub or the underlying computation framework automatically take this trained reinforcement learning algorithm to any other environment, right? Ideally, you train like on your laptop and then you can run the same thing on a drone, right? You just change the underlying computation substrate. And then we have kind of a PubSub implementation, but want to get more towards kind of a more general actor implementation and kind of rewriting the system in Erlang to support some of that. So. And thank you. I have a little bit of code to show as well, because we have all of this on GitHub. I'll just kind of run through that real quick. Oops. So real quick, so we released this library on GitHub that we're working towards reinforcement learning application, but this goes through all the different examples. So really, to get this, all you have to do is run pip install hmslearn. Framework is called Hermes. And then just walking through a simple example, this is a very simple kind of factor graph that for what's called like a hidden Markov model for doing inference. And really all you need to do to get started here is create a file called graph.txt. So let's see, just go. So this is where we just kind of specified basically how the graph topology, as well as oh, okay. Sorry. I don't know if you can. I might just.
That's good.
Sorry. I'm just gonna. This might just be better. It's the same information. So you just specify the edges, the vertices, kind of which update function you're associating with each vertex for variable nodes and your factor nodes, so some product update fact, and then just like an initial state. And then yeah, just import it, a factor graph. Again, this is like an example of some product that I had shown earlier that you can just define in another file. And then really all you need to run is creating this config file. So you just have to specify which algorithm you're using, which PubSub system. It can be Redis, it can be Kafka. Run in synchronous or asynchronous mode, the number of kind of gossip iterations that you want to run, and also kind of if you want to wait a certain time period for things to converge, and then stop. And then just specify where your graph file is, and that's it, and it'll run. So that's kind of where we are with that, and kind of building much more to come.
Okay, so it looks like you're using the nodes in order to define your algorithm.
Mm-hmm.
How difficult is it to really provide, to really encode an optimizational algorithm using, say, comparing it against something like, say, for example, Gurobi?
Mm-hmm.
You know, it looks exceedingly complicated just as a layman looking at this compared to, you know, what we would expect to find in other OR-based systems.
Right. Yeah. Great question. So where we kind of actually want to go with this library is just with this work is just providing you libraries. So here's an integer optimization library. Here's a linear optimization library. And you don't have to actually worry about any of how do you write that in this kind of gossip language. That's kind of should be very, very much under the scenes. But yeah, I mean, we want to make the interface as easy as Groby, like, hey, these are your variables, these are your constraints, and then we'll convert it to a factor graph under the hood, basically. And we've written a bit of code to help you with those conversions as well, so yeah. So that's ideally from the user point of view. This is kind of how it works under the scenes, but hey, you just tell me your constraints and your variables, even as like there's a standard optimization file format, so we can read those in and just convert it from there.
Great.
So a lot of the functions which the factor graph implements, the optimization for, are deterministic or not deterministic?
So it doesn't have to be deterministic, right? Actually, in cases like, for example, stochastic gradient descent, so whether it's deterministic or not actually just depends on whether you run the computation in synchronous mode or asynchronous. So, for example, if you're running, just go back to, whoops, let's see. So I think a good example of that is like stochastic gradient descent, right? So as a factor graph, right? So what I really mean by like synchronous versus like asynchronous mode is, so in synchronous mode, for example, the variable nodes will kind of update themselves, then all send to the factor nodes. The factor nodes will update themselves and all send back to the variable nodes, right? And you just kind of keep doing that one by one. So if you just do that, like let's say you want to implement gradient descent, in synchronous mode you get regular gradient descent, but now if you allow it to be asynchronous communication, so each node basically just sends a message once it's done and doesn't wait for any of the other nodes, then you basically get a stochastic implementation of the problem. And for all the optimization ones, we ran them in asynchronous mode, and it basically all converges after enough iterations to the right answer.
Thank you for the talk, but I feel like this was a bit too math heavy. I was wondering if you could take an example and and then model them as factor graphs,
Yeah.
and then kind of show us what needs to be done in your code with the Hermes framework. That would be good.
Sure. Yeah, definitely. Um, so I'm trying to. One second. Let me find like a good example. Right. So we have for optimization, we've created like a reader. So like I said, there's a standard optimization kind of problem format. So you can kind of even go into like a tool like Garobi, write your optimization problem, and then just export it, and then we can read that in, and then you don't have to do any other work. That's it. But as we're building kind of more and more of these kind of connectors, basically, so in this example, it's a little bit, again, low level. You already have to know that your problem is a hidden Markov model and what that graph looks like. And then once you kind of specify the graph, we can run everything. So really what we want to do is get to the point where this is really all as a user you have to specify, this config file. And then even for the input file, that's where we're building those different connectors. So ideally, you don't have to know about the graph. So we can do that for optimization problems at the moment, and then expanding that to graph and linear algebra and all of that.
Any other questions? No? One more.
How is your work being received? Are you getting invited to speak everywhere? What's going on?
Yeah. So in the process of publishing the work, and I left grad school a little bit early to start a company based on some of it. So what we're actually doing is under the hood, we're trying to make it easy to analyze any type of data, be it time series or discrete data or unstructured data or different types of text and images, because they can all be modeled as factor graphs under the hood. And so that's kind of what we're working on. So this is kind of all the low level work, and underneath is like Redis and PubSub to get it working in a distributed scalable manner. But we're trying to make those interfaces so you don't have to actually worry about, hey, is this time series data, or is this structured data or unstructured? I can give you a quick kind of example with where we're going with this is, I have these different data sets, and again, we create a graphical model representation behind the scenes, and then we can start doing very, very interesting things like, for example, this person doesn't have, so what I've done is, if I just update data, build graphical model, now I can start doing things like, hey, predict what this person's position is. Somebody hasn't entered it in. Production technician 1, right? So this is kind of using that behind the scenes. We're doing all the predictive analytics, and again, time series data. Again, behind the scenes, this is all looks like a factor graphical model to our system. So we can do everything from kind of interpolating values. And this is a plugin we released in the Google Sheets store. Interpolating values of time series. This is an example where there's like a missing, we have 15.92 in our time series, like stock closing prices, but we don't know what date we entered it in, June 2nd, 2011. So that's kind of where we're going with the work, kind of those really, really easy to use interfaces. But the idea is, because we have factor graphs as a universal representation, every data type kind of, and all these different problems kind of look the same behind the scenes, so we can make really easy functionality with that.
Hi. I'm trying to understand what kind of topology you had running this thing. So how many Redis instances did you have? How many clients were connecting to them? What client libraries were using?
Yeah, totally. So for most of our examples, we just use it on a single large instance. So something with, I think most of the parallelism we used was about either 32 threads or 32 processes, depending on the problem. So that's kind of what we would use. And then for very, very large graphs, so for example, in, let's say, PageRank, right? This is, hundreds of millions of edges and nodes. So we wouldn't have in the ideal case, each node or each edge is its own process. But because that's not feasible for problems of this size, we had like a smart kind of partitioning algorithm. So we would basically, group multiple nodes within a subscriber. And then when that subscriber receives messages as a group, it would update the appropriate nodes that are connected to that, and then from there.
So what are the threads? Are they just like a little piece of code that you're running in Python or something?
Yeah, exactly. So pretty much what's running in every kind of Python, depending on if you want a thread or process in Python, it's basically this callback wrapper, right? So each process is basically just a callback. So Redis will publish to it. That process is kind of constantly checking Redis. And then it basically implements, hey, as soon as it receives a message, it updates its state with that message. It computes the outgoing message, and then it republishes the new message. So that's really what every single process is doing. And then the process ID just maps to the node ID. And then you can use the node ID to just look up their state. So initially, we were putting state in Redis, but I don't know if it's changed, but a lot of it was just like single-threaded, so only one thing could access at a time. So that was slowing things down. So we moved state to kind of process memory itself. So in Python, I think we just ended up, the most efficient was we just used Python to just kind of write to memory address, and then we didn't have to worry about too much. But because we were dealing with a lot of kind of NumPy vectors and arrays, there's a lot of pickling and back and forth that made it difficult to actually publish, because you can only publish strings via PubSub. So what ended up working is we would just publish kind of pointers. So that's when we started getting to C, and then to the memory locations, and then we'd look up the actual states or arrays rather than the kind of states themselves. So those were, I think, a couple of the limitations. Is all messages are basically like strings. So encoding like an array, an NumPy array, was very difficult, and you would lose a lot of time pickling and depickling.